Good morning. My name is Mark Reinhold. I'm here to talk about Beyond Java 9. So yesterday I talked about things that are on the slate for Java 9, things about which we're reasonably confident will make it into the release. Today I'm going to talk about things further into the future. They're not for 9. They might be for 10. They might not even be for 10. Who knows? We'll see. Usually I put this slide at the end. I work for a large corporation that has various liabilities and tries to reduce those liabilities by having us display this legal notice in every talk. But today I'd like to call your attention to a couple of parts of this. What I'm about to say is for informational purposes only. It is not a commitment. It should not be relied upon. In other words, all of this is highly speculative. You should give even less credence to what I say than you usually do. All right. Let's get started. So let's consider a very simple class. Point has an x field and a y field. It's a position on the Cartesian plane. How is this represented in memory today? Well, you get an array, if you have an array of these things. What you get is you get an array. It's got a header at the top and then a bunch of elements. And then each element of the array points off to a point object. And each point object has an x and a y in it. So this is, as can be seen, relatively inefficient, right? The references and the headers take up space. In fact, they take up just as much space as the actual data in this example. So it's a factor of 2 just to pay for the space for the pointers and the headers. This might not be a problem if you have an array with only 8 points in it, but if you have an array with 500 million points in it, it could be a bit of an issue. And it's not just about the memory space, right? Whenever you have something that's consuming memory and it's live, then that's very likely going to present more work for the garbage collector, because every time it runs, there's the potential that it will have to copy all of this stuff from one region or one space to another, and that just takes more time. Hi, Kirk. So another problem with this is that dereferences, every time you chase one of those orange arrows, dereferences take time. Sometimes they take a lot of time. On a modern pipeline superscalar processor, having to go to memory can take around 1,000 cycles. And with multiple instruction issue, that winds up being 300 instructions, say. Something like that on average. So if you get really unlucky, because the layout of these things in memory is essentially random. It's not, they're not all nice and compacted, except maybe when they're first allocated. Since it's essentially random, you could wind up in the worst case with all of these things winding up on the same cache line. And imagine you had 1 million of those, then every time you chase a pointer is going to cause a cache miss, which is going to cost you 300 instructions. That's not very good. Now there's a workaround for all this, right? And we've all seen this plenty of times. Yeah, sure. But what you're doing with this, splitting out the x's and y's into 2 int arrays, and you then have to remember that, okay, those 2 arrays go together and whatnot, is you're basically giving up on data abstraction. And you're saying, well, in this case, performance is more important than data abstraction, and people are often driven to this kind of decision. And it's completely understandable. I'm not saying it's the wrong choice to make today, but it wouldn't be nicer if we had a better tool to attack this problem. Because what we really want isn't 2 arrays or an array with pointers to a bunch of individual tiny objects. What we really want is an array of points to be represented like this. We want one array, and we'd like the point values to be inlined into that array, essentially. So there's just one thing. It's one large object. Hopefully most garbage collectors are smart enough to understand that if it's a really gargantuan object, try not to move it around very much. And of course, there are no pointers to chase. You won't be paying cache misses every time you have to access something, potentially. So you might ask, well, modern JVMs, they're really sophisticated and clever. Can't they just do this for us automatically? Well, unfortunately, they can't. And there are several reasons for that. One is that every object in Java is something upon which you can synchronize. Every single object, that's a fundamental part of the object model from the very beginning. It's convenient. It means if you need to lock on something, you don't need to go create a special kind of lock object and then invoke a synchronized operation on that. You can just say synchronized, random object. The cost of this is that the JVM has to be prepared to let you synchronize on any random object, including these tiny little point things, which of course we're probably never going to synchronize on, right? But the potential is there, so you have to have the header and the associated data with it just in case it's going to happen. Here's another problem. If points, is the particular element of the points array equal to a particular point object? Well, it might be. It might not. If the VM automatically inlined our point objects into the big points array, you couldn't really ask this question because there would be no memory address to do the comparison upon, which is essentially how double equals is implemented on objects. It asks, is the address of this object the same as that object? If it is, great. If not, well, then they're not. But there's no memory address. Or maybe there's a memory address and it's inside the array somehow, but that's really outside the scope of Java semantics. It's not C where you can take a pointer to any random thing. Another problem is, well, what if somebody asks for the identity hash code of the object? Identity hash code is an operation that does not depend at all upon the object's content, and in most implementations is computed from the actual address of the object, maybe plus some salt, or maybe it's computed some other way and then cached inside the object header. There are a variety of ways of doing it. But the point is, it's based upon the object's identity. If you ask for the identity hash code of an object once and then ask later, you have to get the same thing back. And to do that, it has to be an object. It can't be a couple of fields inlined into some array somewhere. Where would you keep the information about what the hash code is? In short, the fundamental problem here is that objects in Java have identity. Every object has identity. It has, it has an existence in some philosophical sense, rather than just being, a notional way to treat some part of a larger object. So how can we address this problem? Imagine we could tell, via the language, we could instruct the VM to treat a class as a value rather than an object. So it's kind of like an object, but it's not really an object. So imagine, hypothetical syntax, you could write value class point. What would this get you? Well, the idea here is that by using the keyword value, or whatever the keyword winds up being, this is just syntax, I'm not going to argue about syntax, you get a full-fledged class definition. It has fields, it can have methods, it can have everything that a class can have. It gives you full encapsulation and type safety. Yet it's implicitly final and immutable. You can't change any value, any of the fields once this value, not an object, this value is constructed. So it can be passed by value, it can be allocated in registers, it can be flattened into arrays and classes. My colleague John Rose liked to say, the motto is, it codes like a class, but it works like an int. Since you can inline it, instead of getting this, we can get what we want. The language in the VM can conspire to make for a very efficient representation. So a value class, unlike every other class, and in fact interfaces, does not extend JavaLang object. You can't synchronize on it, you can't mutate it, you can't test it for object equality, you can't invoke system.identity hashcode on it. But in most cases, that's okay. Who needs to test a little point object for equality with another one, by identity rather than value anyway? Okay, so what are value types good for, you might be wondering? Well, they're good for small things. For example, do numeric types. You could imagine you might want an int128 type, a long in C senses. You might want a complex pair, or some kind of decimal type that holds more information than a long, has a decimal scale field on it maybe, but is not so complex and heavyweight as the current big decimal class. You could use it for tuples. So tuples are small, potentially heterogeneous collections of values of different types. Do we need tuples in Java? I'm not sure, but one thing tuples are useful for is multiple value return. And I've seen more good arguments for multiple value return in Java than for tuples, but multiple value return is essentially using tuples to make it possible to return multiple values. So that could be a useful thing there. Value types are useful for algebraic data types, like optional or either. Optional being a thing that contains null or maybe an actual value and lets you test for null before accessing the value or maybe getting a default. Either being something that's it's like a tagged union in Pascal. It's either this thing or it's that thing, and you can ask and figure out which. And then finally, you can use it for cursors or a faster form of iterator, and I'll show an example of that in a moment. What value types are not good for is large objects. It's probably the case that if you have more than, I don't know, half a dozen or a dozen at most fields, then you probably don't want a value type because it'll just wind up being allocated as an object anyway. And on most common modern processors, a value type with more than half a dozen fields probably won't be able to be allocated in registers anyhow. Although with a sufficiently sophisticated compiler could allocate a member of a value type partly in registers and partly not. Okay, let's look at the optional class. So optional was introduced in Java 8, java.util.optional. The motivation for this largely came out of the work on the Streams API, which in turn was enabled by Lambda. Because in Streams there are cases where you need to deal with the possibility of there being a value or no value, but you don't want to pass null because then you'll be checking for null pointers all the time, and that just makes the code hideous. So an optional is a thing that contains a value and methods for getting it or getting something else. The or else method, Venkat has this great line, or else, the most threatening method in the Java platform, or else. So you invoke or else and you pass it a default, some kind of default value, right? If the optional object is holding something, then it'll return you that something. If not, then it will return you the default. So there's no possibility of a null pointer exception here, or no such element exception, or whatever. But if we look at the content of optional, this is aside from the methods, this class is even simpler than point. It's only got one field, and it's a reference to some value. We don't need to allocate an entire object just for an optional. We could just pass this value around, and as long as it stays associated with the type optional, then we'll be fine. So this is an example, interestingly, of using value types for type safety, to achieve type safety over performance rather than abstraction over performance. And in fact, when we did optional in Java 8, we had in mind, well, maybe someday we'll have value types, so we carefully designed optional so that we could insert value there. And there are lots of warnings in the Java doc, do not invoke identity hash code on objects of this type. So hopefully we'll be able to migrate optional to be a true value type in future. So value types are also good, as I mentioned, for lightweight iteration with cursors. How do we do iteration today? Well, there's an iterator interface, and it's got a hasNext method and a next method and a remove method. An implementation of iterator is, well, it's an object. Here's a simple iterator. It iterates over the elements of an array. It has hasNext method and its next method. And it's an object. It's mutable. It takes space on the heap. You have to chase a pointer to get to it. It writes to mutable fields, which can cause more GC pressure. Why is this a good idea? Well, it was actually a very good idea at the time. I'm not saying iterators were a mistake by any means. And in many cases, a modern JVM can actually do enough escape analysis to avoid allocating an iterator object in a very constrained context. But if we do a value analog of this, we can do a lot better. So cursor is a concept it's kind of like iterator, but it's a little different. But the advantage of cursor is that it can be a value type. So here's an array cursor. So imagine we have a cursor interface. I won't bother to show you that. Like Iterator, it has a reference to the array. It has a current offset. It has a not empty method, tells you whether the thing is empty or not. It has a current method that returns the current value, and it has a next method. Now, the next method here, unlike an iterator, it doesn't return you the next value. It returns you the next cursor. Remember, it can't update this cursor because this cursor is just a value, but it can compute what the next cursor will be. And the next cursor has the same array value, and its offset is the current offset plus 1. So only 2 fields, pretty easy to allocate in registers on a modern machine, can be very fast. And here's how it works out in use. Suppose we have an array of strings, we get a cursor for it. Well, the cursor is not empty. We do something with the current value, for whatever do something is, and then we set our cursor variable to the next cursor, and we keep going through that loop. That entire cursor can be kept in registers, and as long as do something, whatever that is, can be inlined, this could be very tight code indeed. Okay, so we've seen how to define value types. One question you might be wondering is, well, can we use them in other kinds of aggregate structures other than arrays? For example, can we write new array list of point, or new tree set of points, or something like that? Well, asking this question is actually pretty much the same thing as asking this question. Can you write new array list of int? And the answer today, of course, is, well, you can't write new array list of int. And you can't because ints are values, not references. So if we want to use value types in arbitrary structures, arbitrary collections, we've got to do something to allow both ints and other kinds of values to be held in them. We finally need to address this fundamental problem Java's had since the beginning of having a small number of value types, now potentially much larger if we have true value types, and reference types. And there's this hard division between them. You can't treat an int in the same way as a capital I integer object. They're fundamentally different things. The root problem here is that polymorphism in Java is based upon the erasure of reference types. This is how we introduced generics in Java 5. It's seen by some as a controversial decision, but I think time has shown it was actually the best one we could make because it allowed for migration compatibility. It made it possible to migrate. If you have a large body of code, you could migrate parts of it over to generics, one at a time. A library you're using from somebody else could remain unmigrated to generics, but yet you could still use it, and vice versa. So generics based on erasure it's essentially a language fiction. The VM knows nothing about generic types today. It's all implemented in the compiler. Type information is erased. There is some information that shows up in class files, but it's mainly for diagnostic purposes. Every use of a generic class, in fact, is implemented by the same actual raw class. So if we have an array list of string, or array list of integer, or array list of URL, if we look at what's going on in the VM, the implementation is the same. It's ArrayList.class, which doesn't know anything about the fact that it's been generified, or what the value of a type variable is in a given instance. So since a variable of type object can hold a value of any reference type, we've got to do something a bit different if we're going to allow a class like ArrayList to work with values, which, well, they aren't references. So the solution is to specialize. The solution is to do a little bit of what C++ does with templates. So in C++, templates are kind of their answer to generics. Every time you use a template in C++, whether the type is a reference type, a value, whatever, what happens is the code essentially gets copied out, and changes effectively made to all the type declarations within it and whatever operators are invoked. And this leads to a fair amount of code bloat. The approach we're investigating now is to do that in Java, but only for types that are values rather than references. So for reference types, we would keep doing that. But when you use something like ArrayList on a value type, we would copy the code on the fly, create a new class that's customized just for that type. So, for example, if you have ArrayList of int, the actual primitive type, you might have a synthesized class, ArrayList, and I've just invented some random notation here, $t equals int dot class. Now, this wouldn't actually exist in the class file. It's just meant to suggest, in the VM somewhere, there would be a class that might have that name. In truth, we expect the ultimate implementation won't actually use that name, but this makes it easier to explain. So each use of a generic class on a value type will be implemented by a different raw class. If we have ArrayList of point, then we'll get ArrayList, $t equals point. If we have ArrayList of complex, then we get another one. In the implementation of all this, at compile time in Java-C, we would continue to generate just a single class file, but we'd add metadata to it to allow the virtual machine to specialize it into various value type classes. At runtime, we'd interpret that metadata, synthesize the specialized classes on demand. And to do that is fairly involved. You need to do things like swap bytecodes and adjust signatures and other stuff. But we actually have a prototype that's pretty much working today. So there's still a problem here, and that is that sometimes existing generic code, and this may sound an odd thing to say, it's not generic enough. All right, if we look at code that's currently in ArrayList, there's a clear method, and the clear method walks through the data and sets each element to null. Well, does this make any sense when you have a value type? I mean, a value type isn't an object, so in fact you can never use null together with an instance, as it were, of a value type, because there aren't really instances of value type. There aren't references. Null is something that only makes sense with references. So we're going to have to make some changes here. In order to make these changes, it will be important, we think, to distinguish classes that are prepared to deal with value types from classes that aren't. So the way we'll do that is by introducing a new keyword called any. So any is a bit odd. In some senses, you can think of it as a supertype, a super type of all value types and all reference types. And some people have asked the natural question, well, why don't you just call that, capital A any and make it a true type? And the answer to that is essentially that it would be such a fiction, it would be very misleading, because for various implementation reasons, we couldn't actually implement that. You could never have something that's purely of type any. So we don't want to go there. So our current thinking is, well, a keyword or some kind of annotation that says this is a generic type variable that not only could be a reference type, but could also be a value type. Now, once the compiler knows that that a value type is a possibility here for the type variable t, it will analyze the body of the clear method and say, oh, wait a minute, you're trying to assign null, and that could be a value, so that's not going to work. So now we solved one problem, we introduced another. How do we get the code to be different? In the case of a reference type in ArrayList, we actually need this code. We need to set all these elements to null so that things will be freed and can be garbage collected. But if it's instantiated on a value type, we can't set it to null because that doesn't even make any sense to ask for that. So what we're thinking of is introducing a very limited form of what amounts to conditional compilation. Imagine you could enclose some code in a block that was keyed on whether a type variable is a reference type versus a value type. Maybe like this. So where ref t means when the type variable t, sorry, that should be a capital T, oops. When that type variable t is a reference type, then include this code in this block, the for loop. If it's not a reference type, then don't include it. Just set size equal to 0, and that's all you need to do. So specialization is opt-in, and then we have this notion of conditional code. The conditional code is useful for solving some other problems that will show up. Elsewhere in array lists, we have the remove methods. So there are two remove methods. They have different return types. One of them takes an int index, and it will remove the element at that index and return that particular element. The second one will take a reference to an actual element, or an actual element value, and we'll scan through the array list, look for that, and remove it. Well, how does this work? Do you think there might be a problem if the value of the type variable t is int? That would be a bug. So if we were designing collections from scratch today, we would probably do this. The remove at that takes an index would, the remove at that takes an index would be called remove at, by analogy with string.char at, etc. And remove would be reserved for the case of removing an element that matches the given element. But now we have a compatibility problem, because existing code could invoke ArrayList on a reference type, and it expects remove of int index to be there. So what do we do? Well, where ref t to the rescue, we can introduce, in the case of t being a reference type, we can introduce a new default method that will turn around and invoke the remove at method. But if you've instantiated ArrayList on a value type, then this won't be there. But that's okay, because anything that's using ArrayList on a value type is new code. It won't be old code that expected the remove of int to be the old remove of int. So conditional code can be used to help solve a variety of other kinds of problems. One that I find particularly intriguing is, suppose you wanted ArrayList Boolean. Now, an ArrayList of Boolean, its default representation would be rather inefficient. You would use a normal array, or if you're lucky, you'll get a byte array. But that's still 8 bits per actual 1 bit that you need. You can imagine a very efficient implementation of ArrayList when, for the case of it being the Boolean value type, such that it really only used 1 bit for every element. So how does all this fit into the big picture? So I've described two specific features we're working on: value types and specialization. But in the bigger picture, what we think needs to be done is how to move Java forward to address kind of the next big pain point. If you look at the history of Java and the bigger changes that have been made to the language over the years, in Java 5 we introduced generics, so that it was possible to abstract over types. In 8, we introduced Lambda, so that it was much easier to abstract over behavior. In 9, we'll be doing modularity to create a secure and scalable platform and provide tools for programming in the large. We think the next big thing, next big general problem area that needs to be attacked is more efficient data layout and more efficient, easier to use access to data. So it's not just about value types and specialization, but also some other features like var handles and a better foreign function interface and improved arrays. So this is all stuff that we're working on in OpenJDK very actively today. There are 2 projects. One is called Valhalla, and that is focused on value types and generics and var handles. The other is Panama, which is focused on a new foreign function interface and data layout control and arrays 2.0. If you're curious about these, you can go to openjdk.java.net, go find these projects. There are documents, there are some initial design documents. There are working prototypes in source code, but they're really bleeding edge. But we're already getting a lot of good feedback on them. So that leaves us with a fair bit of time for questions. Feel free to ask them out loud, or you can tweet me at mreinhold, and I'll read them off the screen. Here's a question already. Oh, hi Dan. What about tearing for large value types? Dan Heidinga works for IBM. He's a JVM implementer. Yes. As I mentioned, you could do tearing, which is splitting the pieces of a value between registers and stack or some other place, if you have a sufficiently sophisticated VM. No guarantees beyond what the Java memory model currently says. Yes, this is a fairly deep question. The Java memory model is quite particular about whether a value can be treated as an aggregate or has to be treated atomically, and it may well be that the upcoming revision of the Java memory model will have to take this into account.
You came very close to mentioning it by name when discussing value types. I was wondering sort of what are the challenges of retrofitting a new top type for value type, or maybe even splitting the hierarchy between value types and reference types, similarly to how it's done in Scala, for instance.
Okay, so I will admit I am by no means a Scala expert. The problem in Java, I think, is that the distinction between references and values at this point is baked very, very deeply into the VM specification. If we provided a true any type or a top type or whatever you want to call it, it would be a pretty bad impedance mismatch between what the language would provide and what the VM would be capable of doing, unless we were to just completely redesign the bytecodes and overall VM architectures. And I kind of don't think anybody's up for that. It's also not clear what a true top type would buy you in practice. I agree that semantically it's kind of elegant. I don't offhand know what Scala's solution to this is. I should go look. But in practice, would it be worth the effort needed to make it be a true any? I tend to doubt it.
Okay, thank you. Second question, if I may. I was wondering, you were talking about cursors and how sort of the pattern for a cursor would be for the cursor to generate new cursors as it sort of iterates over the source data structure. Mm-hmm. So that seems to lend itself very well to the need for some sort of tail call recursive optimization. Is that something that's in the works, or maybe it's already there and I missed it?
No, you didn't miss it. Good question. Yes, there is a natural synergy between cursor-like things and true tail calls. Tail calls are something that I suspect Java will get eventually. I don't think it's the highest priority now. There's been a patch floating around for a number of years that actually implements them in the hotspot VM. There are a few challenges with it having to do, especially with security, because the current security mechanism depends upon the ability to walk the stack to find the security context of each frame. If you do tail call optimizations, well, kind of the whole point is to eliminate a bunch of stack frames. And so you've got to work out what it means for the security subsystem and how to make that work. And we think we know how to do that, but it's a bit delicate and will require some careful engineering. So yes, I'd love to see tail calls someday. But my guess is that we'll see value types and specialization before we see tail calls.
Okay, and there are room for more questions.
Over there. Just wait for the mic, please. It's much easier.
Hi. What about implicit setters and getters?
What about implicit setters and getters?
Will Java have them in any time?
Well, they won't be in 9. Okay, so yeah, we can certainly branch off into other topics. That's also a potential future one. So getters and setters, or I suppose another way to put this is what about having properties in Java, a more efficient, more concise way of defining all the get food, set food methods that you wind up writing in POJAs or that you wind up having your IDE write for you. This has been a pain point for many, many years. We've given it a fair bit of thought. We've talked to lots of folks in the Java community about it. We've looked at what other languages have done, and I think our conclusion for now is every time you ask somebody, well, what would it mean to you to have support for properties in Java, you get a different answer. Some people would be perfectly satisfied with essentially a simple kind of, almost just a macro expansion of, be able to say that, oh, well, this isn't just private int foo, it's, private property int foo, and have get and set methods be synthesized. Maybe you can override them if you want to do something custom, but by default they would just be the obvious get and set methods that would access the foo field. Other people, when you ask them what they want, what properties in Java would mean to them, well, they think properties need to be a first-class notion in the language, that there needs to be built-in language support for not only updating properties and accessing their values, but binding event handlers to them, essentially moving the swing AWT event model into the language. I kind of think that's going too far. Personally, I prefer a much simpler solution. And there are plenty of other variants. Some people would like the meaning of dot to be changed, so that you don't even have to invoke a method. That you can do something. It can work like in Scala, where if x is a property of the type foo, you can type foo.x, and that winds up invoking a getX method, which you can override and provide custom behavior in if you want. But anyway, that's a long-winded way of saying there's no clear answer here. The support in IDEs for synthesizing get and set methods reduces enough of the pain that this doesn't seem to be a real big pain point. Personally, I don't use IDEs very much, so this maybe pains me more than others, typing all these things all the time. But I've made my peace with it for now. Will we fix it someday? Perhaps, but I don't think it's a super high priority. If some idea emerges that is clearly a win, and that most people would be satisfied with, I'd love to see it, but I haven't seen it yet.
Okay, so I have one question. What will happen with autoboxing and unboxing for the simple types once you introduce the value types?
Good question. What would happen with autoboxing once you introduce the value types? Well, if we do this right, it would be wonderful to be able to, essentially, maybe not deprecate and remove, but denigrate the current primitive wrapper classes. So, capital I integer would be a thing that, well, you don't really need to use except for perhaps its static methods, and you could just use int all the time. Or even better, would actually have there be some type relation between int and integer. Whether that's possible is something that we're still thinking about. It's not clear.
Okay, next. How about value? The finalize method for value classes. Can you guarantee that it will be called when when it's popped from the stack?
No, value classes cannot have a finalize method. At least that's our current thinking. We haven't seen a need for it. Arranging for essentially the structure to be invoked when it's popped from the stack. Well, one problem there is a value might not ever even be on the stack. It could just be in registers, and tracking some notion of lifetime so that you can invoke a finalizer at the right point. I can imagine ways to do that, but I'd like to see a large collection of use cases before actually trying to do that.
Okay, still 10 minutes left. Or everyone's longing for a longer coffee break.
Any question? Doesn't have to be about value types, specialization.
Hello. We saw really weird things in the interfaces in Java 8. People creating, I shouldn't mention this here, maybe public final hash maps. That the pointer is immutable, of course, but you can add state in the hash map inside the interface, which doesn't make sense. I have the feeling that we could do that also in value types. And then what would happen if I put some kind of final reference to an object that is mutable itself? I'm not sure if I'm clear on that point.
Let me parse that. So you're thinking of a value type, a value class that has a static field that refers to some stateful object? Not a static field. A value type with a field that refers to a stateful object. Well, sure, yeah, you can do that. I mean, that's essentially what a cursor is, right? It has a reference to an array, which is a mutable thing. That's not a problem. Is there some other sense you were thinking of? Okay.
You talk about synchronization, so no news about concurrency?
No news about concurrency.
Concurrency methods. And
well,
so
let's see. Concurrency is still really hard. I'm not sure. You mean concurrency with respect to value types, or? I mean, the beauty of value types is the concurrency story is really simple, right? It's almost irrelevant because they're immutable and they don't have identity.
Why not have unsigned integers and longs when you do value types?
Why not have unsigned integers and longs? Well, once we have value types, let's see, could you do that? No, you couldn't really because the arithmetic is different. Well, no, you could implement a value type, and if you were willing to do all your arithmetic with methods, then you could have unsigned integers and longs. Go for it. You know, we have looked over the, you know, every few years we've looked at, well, should we do a true, you know, unsigned int or unsigned long primitive type? And this seems to be, you know, one you know, like many decisions made in the early days, it seemed kind of odd at the time, but it's, you know, James Gosling's intuition has borne out. Most things that you need unsigned for, you can pretty much do well enough with assigned ones. And yes, it's awkward, and the arithmetic is a little weird. But the few developers actually deeply understand, and I count myself among them, the arithmetic of unsigned ints in C. It's fairly confusing, and it's not clear that Java needs that kind of confusion. Kirk.
Okay, so I'll ask the question about the other proposals for trying to solve the pointer chasing problem, which is from IBM and from well, a group in the outside of the structured array proposals. Do you see any compatibility between these and the value types, or are these different proposals, or are there ideas in any of these proposals that you think are beneficial to the JVM that would be incorporated, sorry, to the JDK that would be incorporated into these particular ideas that you have here?
Right. So now you're going to force me to give a summary of those two other proposals, and I'm not sure I'm going to get them right, but I'll do my best. So there have been two other proposals that solve some of the same problems. One is this packed objects proposal from IBM, which they've discussed a few times at various conferences. So that was both a language change and a VM change. It was a really interesting prototype. There were lots of good lessons in that work. I think a difficulty with their approach is they were trying to solve problems in two related but distinct domains at the same time. They were trying to solve the efficient memory layout for Java objects problem, and at the same time they were trying to solve the how to give better access to native data that was maybe, you know, allocated and laid out by C or C++ code, or, you know, Fortran or whatever, and it's solving both of those at once. So it was a fairly heavyweight proposal. And you know, we've talked with the folks at IBM about this extensively. I think there are good lessons there, but it doesn't seem like the right solution for Java long term. The object layout proposal this is being driven by some folks primarily from Azul. It's interesting. It's more about the efficient layout problem, and they've taken an approach where it's all done in a library. So their library, you can get it in a jar file, and you can use it on a completely stock Java 8 VM. Now, of course, it won't get you any efficiencies, but if you then patch the VM, and you have to patch the garbage collector and the compilers and many parts of the runtime system to make this work, you patch the VM to intrinsify a bunch of the methods in this library, then you can actually get to a more efficient memory representation. I think our concern about that approach is, I mean, it's cool that you can do it only through API, but it winds up being an awful lot of code you have to write, and fairly unnatural code at that. So you can definitely get there, but it seems to be a pretty cumbersome approach. If we can just have a way to declare, okay, this is a value type, compiler and runtime, please do all the work to make it so, then I think that'll be better. Twitter's weighing in here. Let's see. Will we wind up with C structs? Not exactly, because these are only values. So it's a little bit of the way there. Do you have any plans for pattern matching? Maybe. No, not an area of active investigation, but especially after we get value types and the use of algebraic types like optional and others might be introduced, becomes more widespread, I could definitely see a case for pattern matching, some enhanced form of the switch statement, or who knows what. Operator overloading. Oh yes, that's an old one. Yeah, so value types do once again raise the question of, should there be user-defined operator overloading? If you have an int 128 or a decimal value type, it would be so nice if you could just write plus instead of invoking an add method. So I suspect we will look again at operator overloading, and if we can come up with a limited way of doing it that's not subject to the kinds of abuses that you see in a language like C++, yeah, I think that's a possibility.
Okay, before we have optionals as value types, is it discouraged to use optional as a field type and wrap it as the plain type as optional on usage on a getter or whenever you use it?
Oh, no. You should absolutely use optional wherever it makes sense. I mean, don't think it's the true monadic thing, but it's close enough. Just be careful. If you have something of an optional type, don't test it for object equality. Don't ask for its identity hash code. Don't use it as something you can synchronize upon. Then you'll be fine. If and when it becomes a value type, everything will still work. But I'm sure somebody out there will start synchronizing on optionals, and a related example, even deeper form of that problem is Java lang string. Right, that could be a value type, but it's probably way too late to make it a value type because we know there's code out there that synchronizes on strings. For better or for worse, there it is.
Okay, that was the last question. Our time is unfortunately out.
Okay, if you have more questions, I'll be hanging out at the Oracle booth for a little bit after this. Thank you very much.